Welcome everyone to the second session for this mini course on Gross-Siebert program. You can go ahead.
Okay, so thank you. So maybe just have a very quick review of what we were doing last time. I was talking about the moduli space of stable maps to X. So essentially for us, a stable map is a curve. If you want, you can think of W as just a point, so the C is just a curve, projective curve with nodes. So it looks something like this. Marked points, so you have a number of marked points on the curve. And the map F is a morphism satisfying the stability condition, which says that there are only a finite number of automorphisms of C which preserve the marked points and preserve the map F. And once we have that condition, we get this moduli space of such stable maps. So you need to fix to get a good bounded moduli space. You need to fix the genus of the domain curve, the number of marked points, and the curve class represented by the stable map. So A is a class in the second homology of X, which you can think of as representing the degree of the curve. Okay, so let me go to fresh set of notes since these files get pretty big otherwise. So there's a notion of expected dimension. So the expected dimension of MGN XA, I'll say a few words about what that means, is the following quantity. So it's 3G minus 3 plus N, 3 times the genus minus 3 plus the number of marked points, plus C1 of X, the first Chern class of X, dot the curve class A, plus the dimension of X times 1 minus G. Again, G is the genus of the curve. So what are these various bits here? This is the dimension of the moduli space of curves of genus G with N marked points. That's fairly standard. This number here, this comes from Riemann Roch. And if you have a stable map, if for this, if F from C to X represents a point in the moduli space, one can show the tangent, well, let me be a little bit careful. This is the Euler characteristic of the pullback of the tangent bundle of X. So the idea is more or less as follows. Maybe it's easier to think about these as embedded curves. If you have X and you have a curve C in here, so here I'm assuming that the map F actually embeds C in X, then you can ask, well, how many ways are there of deforming C inside X while we keep the curve C itself? We don't change the isomorphism type curve C. And so the answer is if you have any vector field along C, then at least infinitesimally, you can deform C in the direction of the vector field. So roughly, space of deformations of F from C to X, keeping the domain C fixed, is, or maybe I should say the space of infinitesimal deformations, is the space of global sections of the pullback of the tangent bundle. So that's homomorphic vector fields along C. Now, of course, H0 can jump. It might depend very much on what f star tx is, but the Euler characteristic, which is the dimension of H0, f star tx, minus the dimension of H1 of tx, that is well defined independently of the particular map and is given by the Riemann-Roch formula, which is i.e. is given by this. My pens seems to just okay. Where? Okay, I'm having trouble with my pen again, but it's not because it's not out of charge. So that's the Riemann-Roch formula, which tells you this dimension. So you should think of that as being more or less the dimension of the space of deformation of the map, keeping the domain fixed. And then this is the dimension of the space of possible domains. So all in all, this is the expected dimension. And if life is nice, this will be the dimension of your moduli space. But the fact is that chi might differ from H0, so we might actually have some actual difference between the expected dimension and the genuine dimension. But it's worth noting here, so note if dimension x is equal to 3, and C1 of x is equal to 0, i.e. we're in the Claude-Biot case. Then what does this formula tell us? This is 3 times 1 minus g. This cancels this. This is 0, and we're just left with n. So let's impose further the condition n equals 0. And the expected dimension is always 0. So that's independent of the curve class, because curve class only comes in with its product intersection with the first chain class of x, which is 0, and is independent of the genus because the genus terms cancel. Okay, so that's actually what makes the Claude-Biot threefold case particularly special. You expect that you always have a finite number of such maps. Now, the crucial black box, which I'm not going to go into any detail on, but you should be aware that this black box exists, is that there is a way constructing what's known as a virtual fundamental class. On X. So what is that? That's some class, MGN XA. I usually write it like this, vert. And this lies in the homology, since the expected dimension is a complex dimension. I need to multiply the expected dimension by 2. It lies in the typically the rational homology of MGN XA. So if we were in a situation that the moduli space was the correct dimension, if the dimension of MGN XA is equal to the expected dimension, then this should just be the fundamental class of MGN XA. But the problem is that frequently these things aren't the correct dimension, and so you need something that replaces the correct dimension or the fundamental class of the correct dimensional moduli space. So if the expected dimension is 0, then of course you can consider the degree. This is just an element of H0, and you can consider its degree to get a natural number. So if the expected dimension is 0, then the degree of this virtual fundamental class is just a rational number. And this rationality, rather than being integer, tends to show up because these moduli spaces are delete-monthly stacks, like orbital folds, rather than schemes or varieties. Okay, so let me illustrate where this kind of problem arises. So I already mentioned that for the quintic threefold, if you took the Fermat quintic, then actually you have a number of one-dimensional families of lines. So the expected dimension is not the same thing as the actual dimension. The expected dimension is 0, the virtual dimension, the actual dimension is 1. So you need this virtual fundamental class formalism to extract the number 2875. So the dimension, so if x is, two examples of x is the 0 set of the Fermat quintic, then the dimension of M00 x class of a line is equal to 1, but the degree, the expected dimension is 0, and the degree of virtual fundamental class is equal to 2875. But it's hard to see. I mean, if you don't do this deformation trick where you deform x to general quintic, it's hard to see why you're getting 2875. It's essentially the Chern class of some bundle on the actual moduli space in this case. So this may not have a particularly good meaning. Let me do a second example. So if we have a P1 sitting inside X of Corbière threefold, with a normal bundle, let's call it C, with a normal bundle C and X being OP1 of -1 plus OP1 of -1. So this is kind of the generic situation. Normal bundle of a line in a Corbière threefold will always be degree -2 and can split in a couple of ways. This is the most generic behavior. And then we can consider homology class D times the class of the curve C. This is a class H2 of X set. So we'll consider this curve class. And then M00 X D times C contains maps which take P1, mapping D to 1 to C inside X. So you can take a look at D-fold covers. Now, there are a lot of D-fold covers. This is, in fact, there's a 2D minus 2 dimensional space of such D to 1 covers. All right, I seem to be having some trouble with my pen. There is a 2D minus 2 dimensional family of D-fold covers. That's an easy calculation to do. I'll leave that out, but it's a good exercise to compute that dimension. Now, there's nothing you can do about this, because if I deform the Corbière X to sort of a more, maybe more general complex structure on X, I will still have this curve C. This curve C will always deform with it, and then I will always have these D-fold covers. I always get a modular space that's too high dimensional. Even if you were working in a symplectic world where we could deform to almost complex structure, this curve C survives, and therefore all these multiple covers will survive. So there's nothing you can do to get rid of this positive dimensionality of the moduli space. But you can still compute the degree of, the contribution of this component of the Magi space there will be a connected component of the Magi of this Magi space consisting precisely of these maps. The contribution of this component of the Magi space to the degree of the virtual fundamental class is in fact 1 over d cubed. So this is usually called Aspinwall-Morrison formula. It was conjectured in the original Candelas et al. Paper because they had to guess what the contribution from these multiple covers were. So this is a rational number. There's no way around it. So both rational numbers and moduli spaces that are higher dimensional than you want is a fundamental aspect of this. And in particular, one aspect, you would like to think that when you're doing numeric geometry, when you're doing Grove-Witten theory, you're really counting something. And indeed, for, say, the count of lines in a quintic, you're getting, for a general quintic, you really can prove there are 2,875 lines. If the number you're getting really is counting something, you call that the invariant enumerative. But in general, Grove-Witten invariants are not enumerative. Let me just write that as a slogan. So you have to be careful in interpreting these numbers. But you have to get the right definition for these numbers in order for the Candelas et al. Formulas to be correct. Okay, so that's what I want to say for the moment about Grove-Witten theory. We're going to be returning to fancier versions of the theory in later lectures, but maybe I should stop and ask if there are any questions. Yeah. Okay, so this was meant as kind of a little bit of an introduction to what one needs to do to prove the Candelas et al. Formulas. I'm not going to say anything about how Giventhal and the others actually prove the formulas, because that's a different set of lectures. But now let's move on in our historical survey to what for me is the most crucial point, is also 1996, the so-called Strominger-Yaz-Zaslow conjecture. And this conjecture plays an important personal role for me because I hadn't been doing mirror symmetry until this conjecture came out. And I felt like it was, this is what I've been waiting for to allow me to understand geometrically what's going on in mirror symmetry. So let me give a rough statement of the conjecture. The definition, let X be a Calabi-Yau variety. Calabi-Yau manifold with holomorphic in form omega. So this is our top dimensional form. This is dim x equal to n. And Kähler form omega for a Ricci flat metric. Such metrics exist by Yau's proof of the Calabi conjecture. Okay, so we always have these two bits of information on a Calabi-Yau manifold. If we have a Ricci flat metric, we have the Kähler form, and we have the holomorphic n form. So a submanifold, L contained in X, the special Lagrangian, if first of all, a couple of points. So first of all, the real dimension of L is n, so it's half the complex. This is complex dimension here. So it's not a complex submanifold, it's a real submanifold. it's Lagrangian. What Lagrangian means is that omega restricted to L is 0. This is the Lagrangian condition. And thirdly, it's what we call special, the imaginary part of this homomorphic form, restricted to L is equal to 0. This is the special condition. So being Lagrangian is a fairly soft condition. It's easy to find Lagrangians. It's actually very hard to find special Lagrangian submanifolds. These are volume minimizing. So special Lagrangian, usually abbreviate those as special Lagrangian. Like that, slags are volume minimizing in their homology class. So these are, so if you're on a complex scalar manifold, complex submanifolds are also volume minimizing. So you can think of this as kind of dual mirror to complex submanifolds. Okay, so given this definition, so here's the conjecture, again, very loosely stated. If X and X check are a mirror pair, then there exists dual special Lagrangian fibrations. Right, like this, X goes to B and X check goes to B. Sorry, I should say with general fiber torus. Okay, so this is very vague. Maybe a little bit more precisely, X check B or general B in B, X check B should be the moduli flat U of 1 connections up to gauge equivalence on the torus XB, or put another way, it's H1 of X check B with coefficient R, first cohomology modulo the lattice of integral homology. Sorry, I should not have checks. Okay, so this is a vector space modulo lattice. Okay, so as I said, this conjecture came out in what was very much a physics flavored paper in 1996, but it is a fairly precise mathematical statement. There was a flurry of work on the full strength conjecture sort of immediately after 1996 without a huge amount of progress. One thing we understood not right away, but within 4 years, the work of Joyce and others showed this conjecture couldn't be correct on the nose. But nevertheless, one had hope that it should be right. And a number of us formulated slightly more subtle version of the conjecture, which had a chance of being true. And there has been a lot of progress recently. So work with Yang Li over the last few years has shown the corrected form of this conjecture. for many examples, including the quintic. So that's very recent work. Essentially, there was no progress for about 20 years, and he came in and sort of started to prove quite deep theorems. Now, happily, we don't really need the full strength of conjecture. So part of the issue in this conjecture is that if you do manage to prove the conjecture as stated, it doesn't teach you that much about mirror symmetry. It doesn't really explain why mirror symmetry works. It gives you a geometric relationship between the mirror pairs. And it turns out somewhat softer statements can be just as useful. So for example, you might want X just to be have a Lagrangian fibration instead of a special Lagrangian fibration, and so on. But what we started to do is we started to learn that if you do have a special Lagrangian fibration, that gives you quite a lot of structure on B. And that structure can be understood without actually knowing about the existence of special Lagrangian fibration. So maybe this is now the first into the Gross-Siebert program. So let me state a philosophy. Program. Finding special Lagrangian fibrations. By the way, maybe I was a little bit vague when I said special Lagrangian fibration. Here I define the notion of a special Lagrangian submanifold. What this means is that the fibers are special Lagrangian spaces, because in general they might be singular. So the philosophy here is that finding special Lagrangian fibrations is hard, but we can understand a lot about B without knowing about special Lagrangian fibrations. From B, we can understand a lot about mirror symmetry. Okay. So that is where we're going to really start. So what do we know about B? So B, here's interesting structures. So this comes from the Arnold-Liouville theorem and also work with Hitchin. Hitchin did this work right after the original SYZ paper came out. And now let me start somewhat abstractly and define some of these structures that appear. I won't explain how these structures arise, but if you want, there's a reference expository paper of mine, which explains the transition from the SYZ conjecture to the Gross-Siebert program, which is on the archive. I think this is the archive reference number. Okay, so what is the first structure we're interested in? The definition in affine manifold B is a manifold with an atlas of charts whose transition maps lie in the affine linear group in F Rn. Right, so this is just the group of affine linear transformations of the, so those are things that form X goes to AX plus B. A is GLMR, and B is an Rn. Okay, so it's a particularly rigid kind of manifold because the transition maps aren't arbitrary homeomorphisms or diffeomorphisms, but affine linear. So we say B is tropical if further this linear part is integrals, is an n by n invertible integral matrix. A is in GL and Z for each transition. That's even more rigid, as we can't. That means in particular we can't deform A. A is always discrete. Okay, so why do we like tropical manifolds? So if B is tropical affine, we have a family of lattices which I'll write like this, is lambda contained in the tangent bundle of B. So we have one lattice in each tangent space of B, where lambda is locally generated. By vector fields dy1 through dyn, where yn through yn are affine coordinates. So we have a bunch of charts which give us local coordinates, and any one of these charts gives us y1 through yn. And then the lattice generated by dy1 through dyn is independent of the chart. And this is where it's crucial that we insist that A be in A lie in GLMZ, so that when you change the coordinates y1 through yn to a different set of affine coordinates, this will just change to a different basis of the same lattice. So it will change by this vector, this matrix A. Okay, so it's very crucial that we have tropical conditions, and we also dually we have dy1 through dyn, the differential dy1 through dyn generating locally a family of lattices, which I'll write as lambda check, contained in the cotangent bundle of B. Okay. So okay, so far so good. Now I can use this to get some torus bundles. You can get torus bundles. All right, this is x of B is equal to EB mod lambda. So we take each tangent space of B and we divide out by the lattice of integral vector fields, the lattice generated by dy1 through dyn. And this, of course, projects then to B. And similarly, I can take x check of B to be defined to be the cotangent bundle of B modulo lambda check to B. And notice that these are just dual torus fibrations. If you think of a fiber here as being some vector space, namely tangent space of point, modulo lattice, the fiber here is the dual vector space modulo the dual lattice, which is lambda check. So these are dual in the sense that SYZ fibration wanted. Okay, now we have a little bit more structure. So far, this is purely topological. We have a torus bundle over B, two different torus bundles over B. But in fact, X of B carries a canonical complex structure. And X check of B carries a canonical symplectic structure. So how does that work? Well, easy enough to describe this locally. So the tangent bundle to B locally has coordinates. I think of this as a manifold twice the dimension of M. I can write down coordinates y1 through yn, x1 through xn, where a point which represents a point it represents the tangent vector summation xi dyi at the point with coordinates y1 through yn. So this is just a canonical set of coordinates that you always have. Once you have coordinates in the base, you get coordinates on the fibers, the tangent bundles. And then we can define an almost complex structure. Which I can define by defining a J operator, which acts on dyi equal to dxi, and J applied to dxi is equal to minus dyi. So we just exchange the xi's and the yi's. And just by way of example, if I take B equal to Rn, it's a simple exercise, and which you should probably do for yourself, show that x of B is isomorphic to C star, that's C minus the origin, to the end, so the algebraic torus. So that's kind of the local, and really this gadget is built out of polyannuli inside C star to the n and glued together by monomial transformations dictated by the gluing of affine coordinates. Okay, and then so that's the and then one has to observe that this J descends to the quotient TB mod lambda. Okay, so we're using the fact that any well, the tangent bundle to any manifold carries a natural almost complex structure. The fact that it descends the quotient requires the fact that this lambda comes from an affine structure. And then for the symplectic structure, similarly, the cotangent bundle of B has coordinates y1, yn. They write this x1 hat through xn hat. This corresponds, as before, to the differential summation xi hat dyi at the point y1 through yn. And that's an element of the cotangent space. And then you can write down this, what's known as the usual, what's the standard symplectic form on the cotangent bundle, summation dxi hat, wedge dyi. And this descends also to the quotient EB star odd lambda check. Okay, so from this point of view, we now have, from this affine structure, we now have this fibration, which in fact is Lagrangian, but the fibers are Lagrangian with respect to this symplectic form. And these you might view as being special fibers. So this is a special fibration. And this is this is a Lagrangian fibration. So this is half of the story. We don't have the full special Lagrangian fibration because we don't have metrics on either of these. Okay, but if you do want to get a full picture, there's a way of doing that. Also turn x of B and x check of B into Kähler manifolds. given a choice of a multi-valued convex function K. So in other words, we have some open covering UI and open covering of B. And K, let me write Ki is a convex function on UI, R-valued function, and on UI intersect UJ, Ki minus Kj is affine linear. So they have the same second derivative. Now, if you have such a function K, K pulls back to a Kähler potential. On X of B. So you can use that to define the a Kähler form on K. And this defines a Kähler metric. Defining Kähler metric let's say I'll write the form omega on X of B, which is Ricci flat if the determinant of the matrix of partial derivatives, or the Hessian, if you will, is constant. So it turns out the existence of such functions is crucial for the proof of the SYZ conjecture of Yang-Li's approach. So this is in general an interesting question when you have solutions to these Monge-Ampère equations. So this gives us a Kähler manifold, which I'll write as X of B K, because it depends both on B and K, and X from B K to B is a special Lagrangian vibration. Okay, so we can cook up, if you have this data of B with a strictly with a convex multi-valued function, you can cook up a Kähler potential. And you could get a Kähler manifold. Now, what about the other one, the X check of B? Well, it's easier to explain that in the context of a process called the Legendre transform. So given B and K, we have the Legendre transform B check, K check. So of course, Legendre transform should be familiar to any physicist who's had Hamiltonian and Lagrangian mechanics. This is kind of a slightly globalized version. So we get, given a chart, an affine chart, U containing B with affine coordinates y1 through yn, we have a new set of coordinates given by yi check is equal to dk dyi. So I just differentiate k, and because k is convex, this forms a coordinate system. And you can check easily that on overlaps. For example, if you change k by an affine linear function, yi check is just changing by translation. And if you go to some different sets of coordinates, these yi checks also just change by an affine linear transformation. So this defines a new affine structure on B. We also get a new function, and this is the standard Legendre transform. So we also get k check. I don't think as a function of these new coordinates, y1 check through yn check. This is some y equal 1 to n, yi check minus k of y1 through yn. So if you're familiar with Legendre transform, that should look standard. Okay, so now we've gotten a new affine manifold, a new potential, and it turns out that x check, one can show, x check of B is isomorphic to x of B check. And then we can define x check of BK as being equal to x of B check, K check. Okay, so what that gains for us, remember x check of B was just Lagrangian, so it was symplectic. This is complex. Using this isomorphism, it allows you to transport the complex structure here to a Kähler structure, complex structure here. So now you have a Kähler structure, both the symplectic form and the Kähler, the complex structure. So now, roughly, we have x b k b and x check b k b are dual special Lagrangian fibrations. Okay, so this is a very attractive story, and it's quite possible that if physicists had never told us about mirror symmetry, eventually we would have stumbled on this ourselves. In fact, there was even this sort of notion of affine manifolds with convex functions and Legendre transform that appeared in the literature long before mirror symmetry came along, actually in work in statistics, surprisingly. So there's a basic problem, which is that to be interesting. So here's the nice aspect of this. A nice aspect is completely explains, in some sense, this completely explains mirror symmetry between abelian varieties. So abelian varieties are varieties of the forms that are isomorphic to the Cn modulo some lattice inside Zn, isomorphic to Z to the 2n. All of these, so here we can take B to be equal to Rn, again, modulo some lattice, does lambda prime, and X of B will be one of these abelian varieties. So here B is just a compact torus. Now the trouble is that abelian varieties are a very special case of mirror symmetry, and things like the quintic threefold are very far from abelian varieties. And in particular, these things are always torus bundles, all the fibers are tori, and these will always have Euler characteristic 0. In order to get something interesting that doesn't have Euler characteristic 0, you have to have singular fibers. So this is the bad aspect. get something interesting, we need to allow singular fibers, our torus fibrations. So if you haven't seen this kind of thing before, the typical situation, for example, in 2 dimensions, you would have, so 2 complex dimensions, you would have some 2-dimensional base B, and there would be some points over which you have some fibers that aren't 2 tori, but are pinched 2 tori. So it looks something like this. So over a special point of such a thing, but over a general point, you have a 2 torus. And this kind of behavior does happen. It does happen for K3 surfaces. It's easy to actually to write down special Lagrangian vibrations on K3 surfaces. And they will always have, for example, if all the singular fibers are these pinched tori, you always have 24 of them to account for the Euler characteristic of the K3 surface. So somehow we have to incorporate the singular fibers. Now I want to give you an example in 3 dimensions to show you how this can get rather a bit more complicated. Maybe after I do that example, we'll have a break. So example, a 3-dimensional affine manifold with singularity. So I'm going to allow some locus where the affine structure breaks down. So I'll be a little bit more precise in a second. And this is going to correspond to the quintic. And its mirror. Okay, so here's what I do. I'm going to take a polytope, which I'm going to use the Greek letter xi for because I'm saving delta for the bad locus of the affine manifold. This is going to be the convex hull of the points -1, -1, -1, -1, -1, 4, -1, -1, -1, 4, -1, -1, -1, -1, 4, -1, -1, -1. It's convex hull these 4 points. This is in R4, so it's a little bit tricky for me to draw it. But I'm going to take B. By the way, I should say that peak C, the projective toric variety corresponding to this polytope, is just P4. And if I take a hypersurface, coming from Batro construction, is just the quintic. Okay, so this is a natural polytope to look at if we're interested in the quintic. I'm going to take B to the boundary of C, so this is homeomorphic to S3. It's, of course, being in piecewise linear way. I'm going to subdivide boundary of C into polytopes so that each 2 cell of C or boundary C looks like. So here's a picture that never works very well. I'm going to try my best here. 1, 2, 4, 1, 2, 3, 4. And here's the part that's hard, is you want these things to also line up. Okay, so you can subdivide everything. These can all be taken to be integral points. So for example, if this was -1, -1, -1, -1, and this is 4, -1, -1, -1, this point here, for example, would be 0, -1, -1, -1. Okay, so we have this this decomposition. So we're going to have a lot of 3 cells and 2 cells and so on. Okay, so for every 3 cell sigma in this subdivision, let U sigma be the interior of sigma. Now, sigma is 3-dimensional sitting inside R4. It spans an affine hyperplane. I'll let A sigma be the affine hyperplane spanned by sigma. In R4, and define a chart, affine coordinate chart, by just embedding U sigma inside A sigma in the obvious way. Okay, so what we're saying is actually all the 3-dimensional faces of this decomposition already had an affine structure. We were inside some 3-dimensional affine space. Okay, so that's not too interesting. Now I'm trying to build an affine structure, which means I need to find coordinate charts and then try to cover as much of B as possible. The other thing I'm going to do is around each vertex, for each vertex V, choose a neighborhood UV of V in boundary of C, and define a coordinate chart psi V from UV to R4 modulo the 1-dimensional vector space spanned by V. So we're projecting from V. So this gives another set of affine coordinates. So notice if we're somewhere along here, there's kind of, this is a piecewise linear thing. That this S3 is not linear, but piecewise linear. And when we do this projection, we're kind of flattening things out a bit in some way. Now I have to be very careful about what these open sets UV are, what this set here is, because if I'm not careful, if they overlap, they're not going to be compatible. We'll have something that's transition maps that are only piecewise affine rather than affine. So at this point, it becomes crucial to remove some set from the, okay, so this picture maybe would have been better to have been prepared in advance, but it takes a certain amount of time to draw this, but hopefully the pattern here is obvious. If you look at the reference paper I gave you, you'll find a much cleaner picture of this thing. So what's the point? Is that here, what I can do is I can take, let's find a different color here. I can take, for example, for this vertex V, I can take UV to sort of be this neighborhood here, which doesn't include any of the red stuff. And that way I can choose, if this is V prime, I can choose V prime, again, sort of fitting in here, to be disjoint from V. So as long as I have this red locus separating V and V prime, I can choose UV and UV prime to be empty. Okay, so once I've done this, I get an affine structure away from the red locus. Now keep in mind the picture is really pretty complicated. We have 10 of these 2-dimensional faces that I've drawn here. And along this edge here, along each of these edges, there are 2 other 2-dimensional faces. So actually, we're going to get some other bits of red in those other two-dimensional faces. The picture is really rather a bit more complicated. So we have some vast graph consisting of 10 copies of this picture inside S3. And so taking delta to be the union of all red graphs, and taking B0 to be B, that was the boundary of C, minus delta, we see B0 carries an affine structure. Coming from these charts. Okay, so this is a very hands-on way, very combinatorial way of producing an affine manifold with singularities. So the singularities, affine structure is singular along delta. So we call B an affine structure with singularities, or affine manifold with singularities. So it's quite a complicated beast, but you can construct it. You can also understand, if you want, you can follow the affine structure. If you've gone a loop around each of these edges, you can follow the affine structure, and you can see that there's some kind of monodrome. The sheaf lambda has some monodrome in it, so you can't extend the affine structure across these edges. So let me end the first half with a statement. So there exists. So this is a, I believe, 1999 paper of mine called Topological Mirror Symmetry. So there exists factifications. So we have X of B0 lying over B0, and B0 sits inside B. And so this here is a torus bundle. The point is that we can add some singular fibers in, and we get an X of B. And we can do the same thing for X check of B0. B0, and again, this injects into B, and we get an X check of B. There exist compactifications such that X check of B is homeomorphic to the quintic threefold, and X of B is homeomorphic to the mirror quintic. Okay, so this shows that, at least at a purely topological level, these are topological compactifications, we actually recover at least one case of Batory's mirror symmetry, or the Green-Pesser construction. And it also shows the complexity of what these affine manifolds can actually look like if you actually want to construct them, but they are sort of practically constructible. Okay, so I think that might be a good place for the 10-minute break. Okay, so as hinted by one of the questions, the thing that I want to emphasize here is that this compactification so far is topological, and this sort of result is very soft in the sense that it's really quite easy to build these local models for the compactifications, and then glue these in. Now, on the other hand, this thing is a complex manifold. X of B0 is a complex manifold, and X check of B0 is a symplectic manifold. So we can ask, can one compactify this as a complex manifold? And can one compactify that as a symplectic manifold? The question, let me do this in the opposite order. Can X check of B0 be compactified as a symplectic manifold? And the answer is yes. And this was carried out by two of my former students, Castaño Barnard, that's one name, and Tacey. And the point is that essentially there's no real moduli to Lagrangian torus vibrations. The Lagrangian torus vibration is completely determined by the base, by the affine structure of the base, and that's more or less the content of the Arnold-Louisville theorem, or slightly fancier versions of the Arnold-Louisville theorem. The problem is, the second part is, can X of B0 be compactified as a complex manifold? And there the answer is usually not. And the expectation is, well, there's a lot more moduli to complex structures than there is to symplectic structures. Symplectic structures are soft, complex structures are hard. The expectation is we need to perturb the complex structure by what we usually call instanton corrections, even back in early days of SYZ, by instanton corrections before we can compactify. And roughly speaking, what instanton correction, this has something to do, these should have to do with pseudo-homomorphic, or just homomorphic, if you don't like the word pseudo, homomorphic disks on X check of B0, or sorry, X check of B, with boundary on fibers. So the kind of picture that happens once we compactify, this is going to be very hand-wavy kind of argument, working in 2 dimensions here. Remember, I showed you that we expect to have singular fibers that look like pinched tori, and so a more general fiber is a torus. That you might expect to see homomorphic disks, which fiber over rays in the base or lines, that look something like, so they have boundary on this torus, looks something like this. So it's not a very good picture, but it's vibrating circles over this ray in the base, and then those circles collapse down to this singular point. So this is all very vague, the statement that somehow the complex structure on X of B needs to be corrected by something having to do with these homomorphic disks. But this idea was present already in some early work of Fecha. So let me mention, Fecha had a paper on in 2001, gave two dimensions, a heuristic of how to correct the complex structure. Conservative Solomon in 2004 built on this heuristic to actually give an algorithmic approach. So rather than knowing about homomorphic disks in the mirror, they gave a algorithmic approach. To constructing X of B. This had to be done in the not as complex manifolds. So this is in the category of complex manifolds. This was in the category of non-Archimedean spaces, which is of kind of a form of algebraic geometry where convergence issues become much easier. And then, so this is in 2 dimensions, still two dimensions. And then myself and Siebert in 2007 gave a algorithmic approach. Constructing X of B inside algebraic geometry. Now, the one disadvantage of both of these is that it's not clear. So there are things that look like corrections, instanton corrections, and I'm going to go into more detail of what that looks like. There are things that look like instanton corrections, but they don't necessarily correspond, or we don't see how they correspond to homomorphic disks in the mirror. However, we now have a more sophisticated way of thinking about this, and this is work in 20, I think it was the second year of the pandemic, 21. We have a algebra geometric approach talk about holomorphic disks, and we show these give rise to X of B. So my main goal, I think I'm now a bit more than 3 hours into the lecture series, my main goal is to explain some of the ideas behind this. And what we should see, as I'm now going to sort of start to become much more technical, but we should see as we do this, we should see some of these SYZ ideas that showed up. We should see, for example, affine manifolds with singularities. We should see something that looks like homomorphic disks fibering over rays or more complicated things in the base. We should see convex functions. All of the ideas I've presented so far will still be visible, but in a way that's evolved over the last 20 years, over the last 25 years, to become something that's maybe a little bit less recognizable. But my main goal is to explain this result. Okay, so any questions? So let me now turn to the setting. So far we've been talking about Claude-Biot varieties and talking about mirrors of Claude-Biot varieties. But in fact, even in the early string theory literature, you never got a mirror just by looking at a single Claude-Biot, which is, so rather, mirrors should be associated. So mirrors to Claude-Biots should be associated to maximally unipotent boundary points. And I'll have to explain that. Or usually in the physics literature, the word is large complex structural limit points. Okay, so rather than defining this in general, let me focus on a simpler situation. So in other words, i.e., we should consider degenerations. So I'll look at X over maybe a disk D. So this is a flat family. And for T non-zero, let's say disk centered at the origin, xt, the fiber of this family over T, for T not equal to 0, is a Calabi-Yau manifold. But x0 is singular. So there are some standard examples of this. For example, we could take, let's take a parameter t times x0 to the fifth plus dot 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 plus x4 to the fifth plus x0 times up to x4 equals 0. This defines a family inside A1 with the coordinate t cross P4. And this maps down to A1 by projection of the t coordinate. And as for t equals 0, for t non-zero, this is usually non-singular. There might be some singular fibers, usually non-singular. And if we take a small enough disk center around the origin, we can assume all fibers are non-singular. But for t equals 0, we get just the equation x0 through x4 is equal to 0. We get the union of coordinate hyperplanes. So that's extremely singular. It's about as singular as you can get. Now, the question is, how do you measure this degree of singularity? And you measure it via what's known as the monodromy of the family. So you have, let me try to draw a schematic of this. You have some singular fiber lying over the origin, and you have these general fibers here. We pick some base point T0. This point is the origin. And I'm going to take a loop around the origin based at T0. And we have a monodromy transformation. So this is T from, let's say, the nth cohomology of xt0 with coefficients in Q to itself. So what you do is you take a cohomology class over here, over T0, and you follow it around the loop. And when you get back, you might get back to something different. That's very similar to the monodromy I showed you earlier of the lattice lambda. That was actually the monodromy of the H1 of the torus, of the torus fibers. Okay, so this is a standard situation whenever you study a degeneration. And so general theorem is that T is quasi-unipotent. T is quasi-unipotent. What does that mean? It means i.e. T to the A minus I to the power B is equal to 0 for some integers, positive integers A and B. And B is, and B is always less than or equal to dimension of xt0 plus 1. So is at most one more than the dimension. Now, this A here is kind of spurious because if you go around A times, you go around this loop A times, you just replace T with the power T to the A. And so, in fact, you could go to cover, you can do a covering of this disk completely branched here. And so by replacing the family, by pulling back family via the map, D goes to D, T goes to T to the A, we can in fact assume A is 1. I.e. T is unipotent. So we say T is maximally unipotent if T minus I to the dimension of X T0 is non-zero. Right, so that means that we need to use B equal to dimension X plus 1 in order for us to get 0, in order for this equality to hold. So T is essentially as bad as possible. If you want, you can think of that as saying that T has Jordan blocks given by the size of given by the size dimension. Okay, so that is a typical measure of how bad this degeneration is, and this condition showed up very early on in the mirror symmetry literature, even the physics literature. And the observation that mirrors should be associated with maximally unipotent degenerations was quite an early. So the philosophy is mirrors are not associated to individual Calabi-Yaos, but to maximally unipotent degenerations. Okay, so that is something we need to keep in mind. And when we start to construct mirrors, we'll be constructing mirrors not to a Calabi-Yau X, but to a maximum unipotent degeneration. So now we can assume we have sort of X to D, maximum unipotent. And we have this singular fiber X0 over 0. Now, what I want to do, by the way, let me just say, since I gave this example over here, this is an example of a maximally unipotent degeneration. It is as degenerate as possible. So given such a maximally unipotent degeneration, we want to think about the pair. X0. Okay, what does that mean? Well, it doesn't really mean that much yet, but I want to highlight this because what I want to do is generalize this setting where we have a pair of a variety X and some kind of divisor, in this case, X0. And it turns out, this is one of the things that we sort of came to understand over the last 15 years, that there's a more general setting for mirror symmetry, which is not for Calabi-Yaus, but for pairs of this sort. And in particular, this brings us the notion of a log Calabi-Yau. So let me give the definition of that. The log Calabi-Yau pair is a pair XD where first of all, X is a non-singular projective variety. And D containing X is a normal crossings or simple normal crossings divisor with Kx plus D equal to 0. So the canonical class of X plus D is 0. Put another way, D is an anti-canonical divisor. Now, what does simple normal crossings mean? This means that locally, E is given by equation x1 dot 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 xs equals 0 for x1 through xn, some local coordinates. So in particular, D is in general could be reducible, but it will, for example, in 2 dimensions, you'll just have nodes in D. You'll have something like that. Okay, so that's what simple normal crossings is. Now, I motivated talking about this by first talking about this situation, or this pair. Notice this pair doesn't actually satisfy these properties because X is could be chosen to be projective over D, so the fibers could be projective, but X itself is not projective variety. So I'm going to say some words later how the Claude-Biot situation fits into this more general situation. It turns out that we don't really need this to be projective, but we need fibers to be projective. But let's not worry about that for the moment. Okay, so how about some examples? Well, it turns out that if you take any X, a non-singular toric variety, so remember, so a non-singular toric variety or any toric variety is defined by a fan, and the opens, and that fan is obtained by gluing, right, the toric variety is obtained by gluing together a bunch of open pieces determined by the cones in the fan. And remember that 0 in the fan sigma, that dualizes to the whole lattice M, and then the corresponding open set U0 is equal to spec C bracket M, which is just an algebraic torus of C star to the N. So in other words, every single one of the affine pieces making up a toric variety will contain a copy of the C star to the N, and all those copies are identified on glue. So X will always contain a C star to the N, and we take D to be the complement of that C star to the N. And it turns out that's always an anti-canonical divisor. And maybe I should add the word projective toric variety here, since we insisted that we would deal with projective varieties. So D is anti-canonical.
Sorry, Mark, could I ask a quick question, please?
Yeah.
What aspect of the definition of a Claude-Biot reflects the maximally unipotent condition? Or
Right.
is
So
that
I
not?
haven't. Yeah. So I haven't gotten that to that point yet.
Okay.
So
Yeah. Thank you.
Yeah. So give me a little bit of time. Yeah. So what are these examples here? So for example, we have P2, and the boundary just looks like 3 lines, or remove the coordinate lines. And then another example would be P1 cross P1. So this corresponds to this fan. We have one boundary divisor for each array in the fan. And then here we would have a boundary that looks like 4 lines. Okay, so then another example would be to take P2 with a smooth elliptic curve, so smooth cubic. That also fits into this definition. And then a third example, which is going to be an example, a running example for a while in these talks, is I take P1 cross P1, let me call it X bar. So D bar is this thing here, which I could write as D1 and D2 bar, D3 bar union D4 bar, which I will draw like this, cyclically labeling the boundary. And choose a point on D1 bar and blow it up. Call this point X, blow up X. And now I get something that's no longer a toric variety. You have an exceptional curve that looks like this, and which I'll call E, and take D to be the strict transform of D bar. So that means that D consists of these 4 divisors. It does not contain E. E is not part of D bar. So this is the simplest non-toric example of a log-Calabi-Yau that we could take. Well, actually, this one is also non-toric in the sense that the boundary, the divisor D is not the toric boundary. So because this is simple, so toric, these constructions are very simple for toric varieties. So looking at example as non-toric, the simplest non-toric example will teach you a lot. Okay, so I was going to put that question, the answer to the question off, but let me say a few words. Let me give a definition. We say the boundary D is maximally degenerate if it has a 0-dimensional stratum, i.e., there exists I1 through IS such that DI1 intersect ... DIS is 0-dimensional. In particular, non-empty, because I don't view the empty set as having dimension 0. So, for example, this example, you just take intersection of 2 adjacent divisors, you get a point that's 0-dimensional. Any of these examples are have maximally degenerate boundary, because again, you can find a 0-dimensional stratum intersection of 2 divisors. This is not maximally degenerate. And so now I can tell you that the analog of maximally unipotent is this maximally degenerate condition. So that will be the case where we're going to be able to get a interesting construction. Okay. So in particular, I now want to take this data and construct an affine manifold with singularities. And I'm going to first start without the assumption being maximally degenerate, and then afterwards we'll include that assumption to get the affine structure. So let's have a few auxiliary constructions here. So I'll write the div dx. This is the group of They divisors, or well, let's just say divisors because we're on a smooth ride anyway, group of divisors on X supported on D. So if I write D as a sum D1 up to Dn, then this is just the lattice. This is just the group, free abelian group generated by the DIs. Okay, so just linear combinations of the DIs. And I also, for various reasons, it's convenient to work with a dual. This should look a lot like our setup for toric varieties. This is Hom div d of x into z, which I can write as direct sum I equal 1 to n z, and now with I'll just use di star for the dual basis. And then also I tensor with R to get a vector space. Okay, so now I can define the dual complex. Of the pair XD is a collection of cones in div d of x star R, which I'm going to write as P instead of sigma. P is a set of things of the form summation I in I, R greater or equal to 0, di star. So that's a cone generated by some collection of di stars. And here I ranges over subsets of 1 through n. Remember, the n indexes the divisors, or 1 through n index these divisors. So we have I contained in 1 through n, such that d intersection of I and I of di is non-empty. Okay, and then I'm going to take B, and as you should think B as being the same B almost the same B we saw before. B is just the union of sigma and P of sigma. Okay. So all this records is the intersection pattern, so how the various DIs intersect. So for example, if I take P2 with triangle of curves, then this thing lives inside a three-dimensional space. And of course, D1 and D2 intersect, D2 and D3 intersect, D1 and D3 intersect, but three of them don't intersect. So I get three cones generated by D1 star, D2 star, and D3 star. So I get three cones. That looks like the boundary of the first orthant of R3. Now notice this, the way I drew this looks like the fan for P2. And abstractly, it's kind of a piecewise linear version of the fan for P2. It's sitting inside R3, it's not living in R2. So it doesn't have a full fan structure, but sort of abstractly, it's a piecewise linear cone complex. It's the same. So this is the same as the fan for P2 as an abstract cone complex. And similarly, if I take P1 cross P1 with its toric boundary, that I'm going to get something. Now, this time it's in 4 dimensions, but still looking kind of like the fan for P1 plus P1. But notice if I take this blown up example, then I still get the same picture, except now I've just changed the names of the generators. So this procedure loses quite a lot of information because it can't really tell the difference between this toric example and this non-toric example. You still get something that looks abstractly like the fan for P1 cross P1. Okay, so this is something we can do regardless of any assumptions on D. This just captures the common torics of how the various irreducible compounds in D meet. Okay, so what about an affine structure? So if E is maximally degenerate, then we can put U of B structure of an affine manifold with singularities. Now, I think I propose that I explain this next time, because I should go through it slowly and not rush and do some examples. And so I think since we are almost at 5, that would make this a good stopping point.